Hello, everyone. This is the first lecture, and it will be a combined presentation on sections 1.1 and 1.2. Okay, so by way of introduction, let's consider the following two equations. Okay, so two linear equations and two unknowns. Linear equations in that these equations represent lines in the two-dimensional xy plane. So 2x minus y equals minus 3, and x plus 7y is equal to 1. Now, as long as the two lines represented by these two equations are not parallel, right? I mean, you have two lines in the plane, they're either parallel or not parallel. Parallel when they have the same slope, otherwise they're not. And as long as they're not parallel, then these two lines are going to have a unique intersection point, yes? Right, and what's special about that intersection point of the two lines? Well, whatever those numbers might be at that intersection point, if you plug them into either equation, they will satisfy the equation. In other words, if I put in x equals a and y equals b, from this point it will equal negative 3. Same thing for a and b here. A plus 7b will be equal to 1. and that's the unique point that satisfies both equations. Well, how do you find that intersection point? Well, you should have talked about that in your, algebra classes in high school or in 8th grade or something. At some point you would have covered that, maybe several times. And one way to find that intersection point is using substitutions. So you have these two equations here, and what you do is you take one of the equations, say this one here, and you solve for one of the variables. So x plus 7y is 1, so that means x is equal to 1 minus 7y. Plug that x into here, and I get this. Right? 2 times x, which is 1 minus 7y, minus y is negative 3. And then you just collect like terms. Right? I got 2 minus 14y minus y is negative 3. So minus 15y, and then subtracting 2 from each side, is equal to minus 5. So you do your division, y is equal to 1/3, and x is equal to 1 minus 7y. Right? X is equal to 1 minus 7y. So 1 minus 7/3 is x, so that's minus 4/3. And this approach is fine when you're just dealing with two equations and two unknowns. However, it's unorganized, and it doesn't lend itself to 3 equations and 3 unknowns, 4 equations and 4 unknowns, or 4 equations and 5 unknowns. I mean, we need a more organized approach. Okay, a more organized approach. And the more organized approach, often known as Gaussian elimination, goes basically like this. Okay, let's take an example. So here's a system of 3 linear equations with 3 unknowns. So x plus 2y minus 2z is equal to minus 15. 2x plus y minus 5z is equal to minus 21. And x minus 4y plus z is equal to 18. Right, so 3 equations with 3 unknowns, and notice I have them written in nicely organized rows, right, with the x's in columns, the y's in a column, the z's in a column, the equals in a column, and the results in the column here. One of 3 things can happen with a system of equations like this. Okay, you might get a unique solution. right? Like with the two lines in the previous example, we got a unique solution, a unique intersection point. So here, these don't represent lines. They represent, in 3 dimensions, they represent 3 planes. And 3 planes can intersect in a unique point. You don't have to think about that geometry, but, that's essentially what's going on. Or it might have infinitely many solutions. I mean, there may be a whole bunch of them, and we'll go over examples where that happens. You don't typically get this with 2 equations and 2 unknowns, but with more equations and more unknowns, it can happen easily. Or there may be no solution. I mean, with the lines above, right, if those lines were parallel, which these are not, then they never intersect, so you don't get a solution. Same thing here. These represent planes in 3 dimensions, and those planes could be parallel as well, in which case they never intersect, right, and you wouldn't get a solution. Or there's other problems that can happen as well. All right. And, we'll have plenty of examples of each of the 3 things happening. Oh, by the way, when either of these 2 things happen, so when you have a solution, either a unique solution or infinitely many solutions, in these cases, the system is called consistent. Consistent meaning it has a solution. And then in this case, the system is called inconsistent. All right, so a system of equations can be consistent or inconsistent. Consistent means you have a solution, either one or infinitely many. And inconsistent means you don't have any solutions. Okay. All right. So, what's the organized approach? And this is called Gaussian elimination. We'll talk more about it. The 2 systems of equations are said to be row equivalent when one system is obtained from the other by the multiple usages of these operations. Multiple usages, a sequence of these 3 operations. Exchanging rows, multiplying a row by a non-zero constant, and adding a multiple of one row to another. And these are called row operations. And there's 3 of them. Exchanging rows, multiplying one row by a non-zero constant, adding one row to another row once or several times, or subtracting one row from another row once or several times. Okay, and the theorem is if 2 systems of equations are row equivalent, then they have the same solutions, the exact same solutions. So we won't prove this theorem just yet, although it'll become apparent that it's true, as we go along. All right, so let's go back to that example that we had here, and I'll show you how to apply these row operations. Let's see how long is the video so far. Okay, good. So we have these 3 equations, and we think of them as rows. Row 1, row 2, row 3. Okay, each row has an x in it, and what I would like to do is eliminate the x from row 2 and row 3. So how would I eliminate the x from row 2 and row 3? So what I'm going to do is I'm going to do a new row 2 is going to be equal to the old row 2 minus twice row 1. Row 3 is going to be equal to, new row 3 is going to be equal to the old row 3 minus just 1 R1. So I'm going to multiply this by 2 and subtract it from here. And then I'm just going to take the row originally and subtract it from there. I'm not going to change row 1, I'm just going to change row 2 and row 3. Row 2 is going to be equal to row 2 minus twice row 1. And row 3 is going to be equal to row 3 minus once row 1. Okay? And that'll eliminate the x's from both of these equations. So I didn't change row 1. Row 1 stays the same. Now I'm going to subtract twice row 1 from row 2. So x, 2x minus 2x, 0. Y minus 4y, right? Twice this. Y minus 4y, that's going to be equal to minus 3y minus 5z minus 4z. Right? So I'll multiply by minus 2. So I multiply that by minus 2. So it's going to be minus 5z plus 4z. Not minus 4z, but plus 4z. So that becomes minus z is going to be equal to minus 21 plus 30. Minus 21 plus 30 is 9. All right, so that's my new row 2. Row 3 is going to be x minus x, 0. Minus 4y minus 2y is minus 6y. And then z plus 2z is going to be equal to 3z. And then 18 minus 15 is going to be 18 plus 15 is going to be equal to, what is that, 33? So now I've got a new system of equations that is row equivalent to the first. So the solutions to this system of equations is the same as the solutions to that system of equations. Okay, now let's do another round of row operations. Notice I got rid of the x's here. Okay, now what I'd like to do is get rid of the y's here. Okay, so to get rid of the y's, well, actually first what I want to do is let's multiply row 2 by minus 1/3. Okay, so I'm going to multiply row 2 by minus 1/3. So as to get a 1 in front of the y here. So row 1 stays the same. I didn't do anything to that. And then the second row, multiplied by minus 1/3, that's going to be y plus 1/3 z is equal to minus 3. And then the last row stays the same. I didn't do anything to that. Okay, so now I've got a new system of equations, row equivalent to the second, which is row equivalent to the first. So the solutions here are the same as the solutions here, are the same as the solutions there. So I did some row operations again, adding one row to another, or a multiple of one row to another, multiplying a row by a non-zero constant. That's operations 2 and 3 here. Operation 2 and operation 3. Operation 1 is we won't use it in this example, but in other examples you might. Alright, so now I want to eliminate the y here. So what I'm going to do is I'm going to take a new row 3 is going to be equal to the old row 3 plus 6 row 2. So I'm going to eliminate the y from here. You know, the x was already eliminated. Now I'm going to eliminate the y. So our first row are going to stay the same. So notice we keep rewriting all 3 rows. Y plus 1/3 z is equal to minus 3. And then minus 6y plus 6y is 0. And then 3z plus 2z is 5z. Right? So I multiply this by 6. That gives me 2z. So 2z plus 3z is 5z. And then 33 minus 18 is 33 minus 18, 15. All right, and multiply that by 6 is minus 18. Add it to that, and I get 15. So now I've got this nice sort of triangular shape here. Right? X is only here. So the first variable here is x, second variable here is y, or first variable here is y, first variable here is z. So you get this nice triangular shape to the system of equations there, or this nice sort of, sloping line there. And now I can just read off the solutions. Right? So I start with the last solution. Right? 5z is equal to 15. So z is 3. Right? 5z is 15, so z is 3. Y is equal to minus 3 minus 1/3 z. Right? So, that's this equation here. Y is equal to minus 3 minus 1/3 z. So minus 3 minus 1. So y is equal to minus 4. And in the last one, x is equal to minus 15 minus 2y plus 2z. Right? Minus 15 minus 2y plus 2z. So x is equal to minus 15 minus 2y is minus 6 plus 2z is z is 3 plus 2z is plus 6. No, plus 2z is minus 8. Is that right? So then x is equal to, double check this. I should turn off my email. Oh, minus 15. I see. I put a... No, that's minus 15 plus 2z plus 2z. Oh, sorry. Minus 2y. So it's minus 15 plus 8. All right. Y is negative 4, so that's plus 8. And then plus 2z is 6. There, that's better. So minus 1. All right, so I have a unique solution here. Now you can check that this solution is correct, right, by plugging into all three equations. The three original equations. All right, so what were those original equations? Here they are. All right, there's the original equations. So let's plug those numbers in to those and just double check that we got the right solution. All right, so they were z is 3, y is negative 4, x is negative 1. So minus 1, minus 8, and then minus 6 is equal to minus 15. So that checks out. 2x, so that's minus 2, plus y, that's minus 4, minus 5z, minus 15. So that's minus 19, that's minus 21. All right, so that checks out. And then the last one is x, which is minus 1, minus 4y, so that's plus 16, plus z. So that's 19 minus 1 is 18. So that checks out. All right, so we're correct. So we know we didn't make a mistake there. That is a solution to all three of those equations. All right. So this nice organized way of solving using these row operations, it's still a little bit cumbersome. Okay, there's still something we can do to sort of shorten the process. Okay, so even though this is more than an approach using substitutions, it still can be sort of simplified a little more. There's no need to keep rewriting the variables. Just look at a matrix of coefficients. So, right, we started with this, right? So what we do is we write this as follows. Just look at the coefficients. I have x plus 2y minus 2z equals minus 15. You don't even need these matrix like niceties here, but I'll do it anyway. 2x plus 1y minus 5z equals minus 21. And then x minus 4y plus 1z is 18. And now I can do my row operations on this. Right? I can do my row operations on this thing. So let's do the row operations again, and I'll add a little something to it that we didn't do before. On this matrix. Okay, you don't even need this vertical line here. I just put it there because I kind of like it, but you know that represents where the equal are. So the first column represents variable x, just like it does here. This column represents variable y, like here. And this column represents variable z. And then this column is the results of those equations. Okay, so now let's do our row operations. Let me copy this. Okay, how long is the video so far? 23, okay, good. So I'm going to subtract twice row 1 from row 2, and I'm going to subtract once row 1 from row 3. And that's going to give me this new set of equations. 1, 2, minus 15. I didn't do anything to the first row. I'm just working on the second and third row. So 2 minus 2 is 0. 1 minus 4 is minus 3. Minus 5 plus 4, minus 5 plus 4 is minus 1. Minus 21 plus 30 was 9. 1 minus 1 is 0. Minus 4 minus 2 is minus 6. And then 1 plus 2 was 3. 18 plus 15 was 33. All right, so there we go. And then the next thing we did was to multiply row 2 by negative 1/3. All right, so I took row 2 and I subtracted twice row 1. I took row 3 and subtracted once row 1. And I got some zeros in this column here. And now I'm going to multiply the row 2 by negative 1/3 to get a 1 right there. So first row stays the same. 1, 2, minus 2, minus 15. 0, 1, 1/3, and minus 3. Did I change anything? Sorry. Yeah, that's the same. And then third row, I didn't do anything. 0, minus 6, 3, 33. Okay, you can even skip all these lines I'm doing, but just for effect right now, I'm putting them in. Later on, we'll skip them. Now I'm going to do row 3. I'm going to take row 3 and add to it 6 row 2. I'm going to add 6 copies, 6 times row 2 to row 3 to make a 0 there. So first row stays the same. Second row stays the same. I'm only modifying row 3. 1/3 minus 3. 0 minus 6 plus 6 is 0. 3 plus 2 is 5. And then 33 minus 18 was 15. All right. Now what I'm going to do, so this is where we stopped last time. Okay, this is where we stopped last time. But let's keep going. Let's put a 1 right there. It's nice to have that leading coefficient to be a 1. Okay, so I'm going to do row 3 multiplied by 1/5. So first row stays the same. 0, 1, 1/3, minus 3, 0, 0, 1, 5. Okay? Or 3. Dividing by 5, and I get 3 there. Now, you could stop here, but actually I want to go further. What I'm going to do now is I'm going to take this one here, equation 3, and I'm going to make zeros in the column, in the third column here. So what I'm going to do is I'm going to take row 2, and I'm going to subtract from it 1/3 or 3 to make a 0 right here. And then I'm going to take row 1 and I'm going to subtract from it, or add to it, twice row 3. So after I do that, I'll eliminate these two entries here and make zeros. Okay, and I'm going to leave row 3 the way it is, because the row 3 just says what? This just says z equals 3. So we already know what z is, right? So then we could do that sort of back propagation that we were doing up here. Right, this sort of back substitution job, but even that we make it more organized in this matrix approach. Okay, so all right, row 1, and because there's zeros here, it doesn't affect what's going on there. Right, I got 1 minus 0 minus 0 minus 1/3 of 0, so that's still 0. All right, well let's take care of row 1 first. 1 plus twice 0 is still 1. 2 plus twice 0 is still 2. Minus 2 plus 2, 0. And then minus 15 plus 6. Minus 15 plus 6 is minus 9. And then 0, so 0 minus 1/3 0 is 0. 1 minus a third 0 is still 1. And then 1/3 minus 1/3 is 0. Right? And then minus a third minus a third of that. So minus 3 minus 1 is minus 4. And then the third row stays the same. Right, so this says z is equal to 3, y is equal to negative 4. Z is equal to 3, y is equal to negative 4. And then for the last one, I'm going to do row 1 minus twice row 2 to get a 0 there. So I've got 1 minus twice 0. That's still just 1. 2 minus twice 1, that's 0. And then 0 minus twice 0 is 0. And then the last one, that one's going to be the important one, minus 9 minus twice that. So minus 9 plus 8 is minus 1. 0, 1, 0, minus 4. Row 2 and row 3 stays the same. And there it is. So this says that x is equal to minus 1. Y is equal to minus 4. And z is equal to 3. All right, so that's our final solutions. And the same one as we had before, right? Minus 1, minus 4, 3. X is minus 1, y is minus 4, z is equal to 3. All right, so this nice form here, you have a 1 in every row and a 1 in every column, and you just from there just read off the solution just straight like that. Give me a moment, I'll be right back. Okay, let's look at another example of a system of equations. Find the solutions to the following system. If they exist. Alright, so we're going to have x minus y equals 10. X minus z equals 7. And y minus z equals minus 3. So the matrix that goes along with this, okay, the matrix of equations here, 1x minus y, minus 1y plus 0z equals 10. 1x plus 0y minus 1z equals 7. And then 0x plus 1y minus 1z equals minus 3. Right? Just like before. So now I'm going to subtract row 1 from row 2 to get a 0 here. Right, I've already got a 0 here, but now I want like a 0 there. So first row stays the same. And then I didn't change that. I'm just changing row 2. Row 2 minus row 1. So 1 minus 1 is 0. 0 minus minus 1 is plus 1. Minus 1 minus 0 is minus 1. And then 7 minus 10 is minus 3. And then 0, 1, minus 1, minus 3. So now I'm going to try to get a 0 here. So I'm going to subtract from row 3, row 2. And probably you can already see what's going to happen. It's just going to, you know, the rows are equivalent, so it's just going to just 0 out the whole third row. So 1 minus 1, 0, 10. 0, 1, minus 1, 3. And 0 minus 0 is 0, 1 minus 1 is 0, minus 1 minus minus 1 is 0, minus 3 is 0. So I have a leading 1 in the first row here, a leading 1 in the second row here, and row 3 is essentially gone at this point. Right? What does row 3 represent? This just represents the equation 0 equal to 0, which essentially tells you nothing, gives you no information. So I got this leading 1 here. What I'd like to do, just for convenience, is eliminate this right here. So I'm going to add to row 1 row 2. So 1 plus 0 is 1. Minus 1 plus 1 is 0. 0 minus 1 is minus 1. 0 plus minus 1 is 1. And then 10 plus 3 is 13. Second row stays the same. And last row is just zeros. So what are we left with here? So essentially our 3 equations with 3 unknowns really boil down to only 2 equations with 3 unknowns. Right? 2 equations with 3 unknowns, because that third equation was really just a combination of the first 2. So I didn't really have 3 equations. The third one was just sort of a repetition of information of the first 2. And this elimination method basically reveals that to us, that third equation didn't tell us anything that the first 2 didn't. So what we're left with here, x minus z is 13. Oh, so yeah, x minus z is 13, and y minus z is equal to 3. So what we do is we say the following, right? So the z is in both equations, right? The third variable is in both equations, and the first 2 variables are in each equation once. Right? So this says x is equal to 13 plus z, y is equal to 3 plus z, and then we say z is free. So z is free, that is anything. Z equals anything. No constraints on z. And whatever you choose here is going to be a solution. So we have infinitely many solutions. Right? Z equal to 0, x equal to 13, y equal to 3, z equal to 1, x equal to 14, y equal to 4, z equal to minus 2, x equal to 11, y equal to 1. Right? These are all solutions. Whatever number I choose for z is going to give me a new solution for x and y. And all of these solutions will satisfy that original set of equations, the original system of equations. Okay? So when you're doing this row elimination process, okay, these row operations, you know, for a unique solution with 3 unknowns, you need 3 equations. For a unique solution with 4 unknowns, you need 4 equations. But if one of your equations is sort of a repeat or is dependent upon the first 2, then one of those equations essentially gives you no information. Okay, so in general, what happens is the following. So in general, if we have n unknowns and m independent equations, whatever independent means. We'll make that more precise later. Then our solution set, in M, we'll say M less than or equal to N. If M is more than that, then there's additional sort of weirdnesses that happen that, again, we'll talk about later. Then our solution set will have N minus M free variables, like in this previous example. Freely chosen values. Okay, so up here we had 3 unknowns and 2 independent equations gave us 1 free variable. Okay, and when you organize it like this, you have a 1, the leading coefficient of 1, and zeros and everywhere else in the column, leading coefficient of 2 and zeros everywhere else in the column, and then the free variable is here in the last column. All right, what about an example that doesn't have any solutions? Well, if we just like tweak that guy, that first this example here just a little bit, we can get an example like that. So what I'm going to do is I'm going to change this here to let's just put a -1. All right, so we put it in matrix form: 1, -1, 0, 10, 1, 0, -1, 7, and 0, 1, -1, -1. All right, I'm going to take row 2 and subtract from it row 1. So 1, -1, 0, 10, 1, 0, -1, oops, no. 1 minus 1 is 0, 0 minus 1 is 1, -1 minus 0 is -1, 7 minus 10 is -3. 0, 1, -1, -1. So now I want to make a 0 here, so I'm going to do row 3 minus row 2. And what we get here is the following. One minus 1 is 0, -1 minus 1 is 0, and then -1 plus 3 is 2. Right, so in this last row, the last row says that 0 is equal to 2. Right, which of course is not the case. 0 is not equal to 2, so the system is inconsistent. That is, no solutions. Okay, so in doing these row operations and reducing to this diagonal or triangular form, you end up with some sort of contradiction, some sort of contradictory information. 0 is equal to 2 or something of the like. Okay, so this system of equations has no solutions. Oops. All right. So let's formalize some ideas we've been using here. So a coefficient matrix is in echelon form when the first non-zero entry in each row is strictly to the right of the previous rows. So something like this is in echelon form. So 3, 1, 2, 1, minus 1, 7, 0, 0, minus 3, 1, 5, 0, 0, 0, 0, 1, 2, 0, 0, 0, 0, minus 3, 5, 2. So this is in echelon form. The first non-zero entry in each row occurs strictly to the right of the rows previous to it. Not immediately to the right, okay, strictly to the right. Right? I mean, so here we skipped a couple columns, and here we go down by one column each. And you could have zeros. Let's just make a zero row or something like that here. Right? So this is in echelon form. Okay, so your row operations are geared towards getting your coefficient matrix into echelon form. Even better, a coefficient matrix is in reduced, row echelon form. Also column echelon form. Row echelon form. A matrix is in reduced row echelon form when it is in row echelon form with the first non-zero in each row being a 1 and the columns containing these leading coefficients are 0 everywhere So, for example, this is in echelon form, row echelon form. Reduced row echelon form, okay, there's a few more conditions. The first non-zero entry in each row is not, just some non-zero, it's a 1. So that's a 1, that's a 1. And then everywhere else, in every other, so in the column that has the leading coefficient, right, it's 0 everywhere else. Right, so the whole column that has the leading coefficient of 1 gets zeroed out except for that 1. Let's make this a 3 for a little difference. Right, so that's reduced row echelon form. Okay, the leading coefficients go strictly down to the right, and then in each column that has a leading coefficient, every other row is 0. Okay, so that's a reduced row. So when you're doing your row operations, you have an eye towards getting your system of equations down to a system of equations in reduced row echelon form. So once you have a system of equations into reduced row echelon form, then you can just read off the solution. Is put into reduced row echelon form. Row these solutions can be read off the matrix. Can be easily read. So, for example, if you had a unique solution, it looks like this: 1, 0, 0, 0, 5, 0, 1, 0, 0, minus 3, 0, 0, 1, 2, or not 2, 0, 2, 0, 0, 0, 1, 2. So here we have 4 variables. And we dispense with this notion of using x, y, z as variables, or w, x, y, z. Doesn't mean eventually you run out of letters to use. You just say that the 4 variables are x1, x2, x3, x4. So here we have x1 is 5. Right? We have 5 equations and 5 unknowns. 5 independent equations. And the equations is just this very simple equation. x2 is minus 3, x3 is 2, and x4 is 2. All right, unique solution. Unique solution, right? You have like n unknowns and n equations, independent equations. Right? Or if you had something like this, 1, 0, 3, 0, 5, 0, 1, minus 2, 1 is minus 3, 0, 0, 0, 1 is 2, and 0, 0, 0, 0, 0. So here I've got leading coefficients here, here, and here. Oh, and we're in reduced row echelon form like this. All right, I have leading coefficients in these columns, and the columns are 0 in every other entry. Okay, so I have a 1 in the first row of first column, a 1 in the second row of the second column, and a 1 in the third row of the fourth column, and then all zeros underneath that. Okay, so this, all right, so we've got 4 unknowns, x1, x2, x3, x4, and 3 equations. Right, so we're going to have 4 minus 3 equals 1 free variable. Which one is it? It's the variable corresponding to the column that doesn't have the leading coefficients in it. Right, so there's no leading coefficient in here, so that's the third column, free variable x3. Right, so I got that x3 is free, x4 is 2, so let's do it in order there. X4 is 2. X3 is free, so that's the one that doesn't have the leading 1 in its column. X2 is equal to minus 3 plus 2 x3. Right? And x1 is equal to 5 minus 3 x3. Right? So that's your set of solutions. maybe let's look at these again. X2 minus 2x3 is minus 3, and this one says that x1 plus 3x3 is 5. So then we write down the solution. X1 is equal to 5 minus 3x3. X2 is equal to minus 3 plus 2x3. X3 is the freely chosen variable, and x1 is equal to, or x4 is equal to 2. So nothing free about the x4, but the x1, 2, and 3, they can vary. All right, so that's infinitely many solutions. With one free variable. You can always have more, but you just have one in this instance. Okay, so that's the lecture on section 1 here, and that's the end of it.